want to thank you all for coming this morning. I realize I put my videos online, so it's really awesome you guys are willing to take the time to come into this early lecture and get the day started. Last week I talked about vinyl gloves, and one of the learning assistants, Don, was holding up this box of vinyl gloves, so we talked about the polyvinyl chloride in there. But way earlier in this quarter, we had noted that in our discussion section room, they have these bottles of disinfectant in those rooms. And one of the students, Jack, was in there holding up this bottle. And you can see that it's talking about the ingredients in this disinfectant spray that they've provided, probably in most of the classrooms around the UCI campus. And it says that this spray is a non-acid disinfectant cleaner that acts as a disinfectant, a cleaner, a mildew stat, a fungicide, a viricide, a deodorizer. It does everything. And so what's in here that's making it do all that stuff? Well, the fact is this is mostly water. It's 99.99% water. But there's a tiny amount of something in there that seems to have all these properties. And if it's only a tiny amount, it must be very potent or reasonably potent. So let's go ahead and take a look at these active ingredients that allow it to kill I'm not sure if I should use the word kill with a virus, but to deactivate so many different types of potentially infectious agents. So when you look at the ingredients on that bottle more closely, it says that it's a mixture of a bunch of ammonium chlorides. Cetyl benzyl dimethyl ammonium chloride. The cetyl group is just a long chain with 16 carbon atoms. A myristyl group is 14 carbon atoms, and a lauryl group is 12 carbon atoms. And so it just looks like a whole mixture of these ammonium salts with different size, different lengths, carbon length chains. The other type in here has not just a benzyl group on there. These other types have decyl groups, octyl, decyl, dimethyl. So you can tell here that they're listing 4 different groups: cetyl, benzyl, and 2 methyls; myristyl, benzyl, and 2 methyls; lauryl, benzyl, and 2 methyls; octyl, decyl, and 2 methyls. So all of these are what we call quaternary ammonium salts. They are not protonated in any way. They've got 4 bonds to nitrogen. And whenever you have 4 bonds to nitrogen, whether it's a nitro group or an ammonium group, it's going to have a positive charge, a formal positive charge on the nitrogen atom. Let's take a look at these chemical structures. These first 3 are commonly sold and commonly used as a mixture called Benzalkonium chloride. When I was a postdoc, I used to do tissue culture, and when we were done with all of our nutrient-rich media and cells and stuff, we'd dump them, all the glassware and plasticware, in a big tank of aqueous benzalkonium chloride, which kills, disinfects everything that's there. But the other section of the ingredients in here are these other quaternary ammonium salts, and you can tell they've been designed to have very long chains. So let's go ahead and take a look at what these things are doing to kill so many types of cell types or deactivate viruses. So what are these quaternary ammonium salts doing? They are membrane disruptors. That's the whole function here. They're designed to have long chains so that they can kind of slip their way into biological membranes, phospholipid bilayers. You know that phospholipid bilayers, I would guess you would know from some classes you've taken in biochemistry, that phospholipids have a negatively charged phosphate group on there. And so these quaternary ammonium compounds just love to hang out near that negatively charged phosphate carpet on phospholipid bilayers. And once they do that, these long alkyl chains get in there into the lipid bilayer and they disrupt the membrane. And that disrupts ionic balance, things leak out of the cells, bad things get into the cells, and that leads to cell lysis and death. And rather than taking a chance on some kind of cell becoming resistant to just one of these, they use this whole big mixture so that no cells can become resistant to this effect. So this is effective not just against bacteria, like gram-negative bacteria that have all these biological phospholipid membranes, but also against enveloped viruses, such as the SARS-CoV-2 virus. That's why they put this in all of these classrooms, is the SARS-CoV-2 virus has a phospholipid bilayer membrane that it stole from the host cell. Same is true for the flu, influenza virus, and other types of bacteria and fungi. Now, what kind of surprised me, my daughter just got a cold, a really awful cold this past weekend, just took her down for 3 days. And the common cold, rhinovirus, doesn't have an envelope. It's just pure protein capsid. And so that means that this type of spray is completely ineffective against probably the most common viral infectious agent, which is the common cold. And so I'm wondering how they can advertise on this bottle that it's effective against viruses when one of the most common viruses that affects humans it doesn't work. When you look closely at the label, they put an asterisk here on viricide, just to make it clear it doesn't work on all viruses, just on some of them, COVID and flu. And I guess that's enough, but it's not going to help you clean anything off. You're going to get a cold from somebody if they touch something, whether it's been sprayed or not. All right, this sets us up to talk about our last chapter in this course. So we're entering week 9 next week. This is the end of week 8. Week 9, we've just got one chapter left to cover. Really, the past 2 chapters on enolate chemistry are the real meat of our next exam, exam 3, that's coming in a couple of Fridays. But the amines chapter is phenomenally important if you're interested in drugs, if you're interested in biochemistry. And so we really have to pay attention to the things that are in this chapter. Let's go ahead and take a look at 2 functions of amines. When I talk about amines, I'm interested in chemical reactivity as well as physical properties. But let's go ahead and take a look at 2 chemical reactions where you will see amines get involved. So the first one is that amines, and let's take a look at the business end of the amine. That's that electron lone pair on the amine. So the first and most obvious, I think, and most important thing is that amines can act as bases. When I use a base in my organic reactions, I don't use sodium hydroxide. That's not soluble in organic solvents. We use triethylamine and pyridine as our common bases for organic reactions because those are soluble in organic solvents. So when I see an amine and I refer to it as a base, I'm specifically telling you what it's going to do. That means it's going to pull a proton off of something, right? So when I talk about having a base and I draw an amine, there's going to be some sort of a proton transfer. And that's going to lead to an ammonium salt. That's going to put a 4th bond, that's supposed to be the number 3 there. That's going to put a 4th bond on nitrogen. When you have 4 bonds to nitrogen, the nitrogen will have a formal positive charge. You'll generate the conjugate base of whatever your acid was. And the important part about these acid-base reactions is that they are fast and they are reversible. Fast and reversible. And this gives amine an essential property that is important for drugs. If you look at the list of the top 200 prescription pharmaceuticals that were designed and synthesized by organic chemists who sat in a class just like this, amines appear on almost all the drugs. And that is because amines have this property of being protonated and then deprotonated very easily. Protonated, deprotonated. Why is that important? Because amines that are neutral molecules can easily slip into biological membranes and cross biological membranes. Biological membranes like phospholipid bilayers are designed, they are an ingenious design that keep out charged molecules. But only charged molecules tend to be soluble, but only neutral molecules can cross membranes. Man, those biological membranes have got you coming and going. You're never going to design a molecule that can cross a biological membrane unless it has this amazing property where it can be soluble in water, like the ammonium form, but then neutral so it can cross the membrane. And that's why amines are common in so many pharmaceuticals. Okay, so acid-base reactions, always with amines, always fast, always reversible. And so it's just a matter really of the equilibrium constant for us to talk about. But let's talk about a different function of amines. When I see an amine, it can also do a second thing. And that second thing that it can do is it can attack carbon. It can attack carbonyl groups. It can do SN2 reactions. And when I'm talking about attacking carbon, let me use my red pen here because I love red pen for these arrows. When I talk about attacking carbon, that means I'm talking about it being a nucleophile. I will use the word nucleophile when I'm talking about a nitrogen lone pair. Same nitrogen lone pair I just talked about above. But when I talk about a detectant carbon, I'm going to refer to that as a nucleophile. And compared to reactions of protons, these reactions are not as fast. It's just harder to form bonds to heavier atoms. It's slower. Bonds to heavier atoms vibrate. You know that. You just look at an IR spectrum. You can tell they vibrate more slowly. And the byproduct in this case would be some sort of an anionic leaving group. These reactions are generally not easily reversible, so at least not to the extent of protonation. So two important reactions of amines that we're going to talk about in this chapter. Amines as bases and amines as nucleophiles. Now, I want to make it absolutely crystal clear. When I talk about an amine, I am not talking about an amide. An amide is not an amine. I won't call an amide an amine, and I won't call an amine an amide. And what's the fundamental difference there? Well, an amide has a carbonyl next door that just sucks the life out of that nitrogen lone pair. So, right, that nitrogen lone pair isn't going to attack anything. It's not going to pick up a proton from anything because that nitrogen lone pair spends all of its time donating into this carbonyl group. There's 40% double bond character here. That's how important that donation is. So when I talk about an amine, or if I draw something that looks like this, and I draw an R group here, that's not equal to an amide. R group means it's an alkyl group or something that doesn't have a carbonyl or a resonance acceptor on there. So let's make that clear. Amide nitrogens, that's not the business end of the amide. The business end of the amide is that oxygen atom. That's where you protonate. That's where that part that acts as a nucleophile when it does. Okay, let me circle these charges because it looks a little bit like a bond, and I'll just make it clear that those represent formal charges. All right, this is our chapter. And when I mentioned in the last lecture, when I think of amines, I usually think of illegal drugs like methamphetamine, heroin, morphine, those things. That's the characteristic functional group in all of those illegal drugs. All right, we're going to mess you up in this chapter because I'm going to use a type of nomenclature, whether I want to or not, because I don't expect you to know IUPAC nomenclature, but I expect you to be able to discuss functional groups and know the names of functional groups. And there's a type of naming system that we use where we describe things like carbocations and alcohols as primary, secondary, or tertiary. And we're going to use that same kind of naming system to talk about amines. I'll say, oh yeah, that tertiary amine, triethylamine. And I expect you to know what I mean when I say tertiary amine. I'll say that secondary amine, morpholine, it's a cyclic secondary amine. I expect you to know what a secondary amine is. Let me explain to you why this is going to screw you up. And this is the stupidest naming system ever, but I kind of see how they ended up with that. So I hope you know what a primary and secondary and tertiary carbocation is. You might recall we talked about things like this. We described this as a tertiary carbocation if there's 3 alkyl groups on here. So you've used this tertiary, primary, secondary naming system to describe alkyl halides, to describe carbocations. I don't know why I have 2 pluses on there. Let me erase one of those. That's kind of disturbing. That's bothering me. Oh, there we go. Okay, got rid of that. Let me put that tertiary there. So you've used that naming system before. And you've used this naming system for alkyl halides and alcohols. Let's go ahead and take a look at that over here. So if I look at this alcohol over here, we would refer to this as a primary alcohol. See that carbon atom right there? We call that the carbonyl carbon of an alcohol. It's got 1 alkyl group on there, so we call that primary. So whenever there's 1 alkyl group, we call that primary. If there's 2 alkyl groups on here, we call that secondary. And if there's 3 alkyl groups on there, we call that tertiary. And that makes sense. It's just like a carbocation. If there's 3 alkyl groups on the carbocation, here, here, and here, then that's a tertiary carbocation. So now let's come down and look at amines, right? That primary, secondary, tertiary naming system you've been using. If I take ethylamine down over here that has 1 alkyl group on the carbon that's attached to nitrogen, we call this a primary amine. And that makes sense. We come down over here to this other amine, isopropylamine, that has 2 alkyl groups on that carbon, and we call that a primary amine. And then we take T-butylamine that has 3 alkyl groups on here, and we call that a primary. You see the problem here? It doesn't make any sense. For some reason, they've suddenly decided they're going to completely change the naming system on you. And this is stupid, and it's going to cause some confusion when we talk about it. So let me try to clarify how we use this primary, secondary, tertiary system when we talk about amines. So for an amine, let me go ahead and change this to black pen here. So for an amine, if I take this same amine with a T-butyl group on here, and I put a second alkyl group on the nitrogen, now it's a secondary amine. This naming system is used to describe how many alkyl groups are attached to the nitrogen, not to the carbon atom. So if I want to talk about a tertiary amine, like triethylamine is the most common one that we'll see, right? There's 3 alkyl groups now on the nitrogen atom. This one we call a tertiary amine. So this primary, secondary, tertiary doesn't have to do with the carbon that's attached to nitrogen. We use this primary, secondary, tertiary system to describe how many alkyl groups there are on the nitrogen. There is one last type of amine name, and it's not an amine. It's not an amine. It's this quaternary ammonium type functional group. The same one I just talked about with that benzalkonium chloride and all of those antiviral, antibacterial agents that they put in those spray bottles. Those are quaternary ammonium salts. Acetylcholine, the neurotransmitter that you have at neuromuscular junctions, that contains a quaternary ammonium salt. And you can't deprotonate the nitrogen to get rid of that positive charge. That positive charge is stuck there 100% of the time on these quaternary ammonium salts. Now, there is a section on physical properties like boiling point and I'm not going to ask you about things like boiling point. Feel free to read that. It's not something that I would ask you about on my exams. But I will expect you to know things related to solubility. Charged things are soluble in water, and neutral molecules are soluble in organic solvents. That is a physical property I expect you to know about. All right, let's talk about the structure and bonding of amines, specifically related to stereochemistry. We've talked about stereogenic centers and stereochemistry, and I tell you that you are on the answers on my exams that you're expected to know, be able to identify stereogenic centers in the presence of stereoisomers. So let's go ahead and talk about how many things you can have on a nitrogen that is sp3 hybridized. So you should already know that whenever you have a carbon atom with 4 different groups attached, then that carbon is a stereogenic center if it has 4 different groups attached. And you can assign Kahn, Ingold, Prelog configurations, RNS configurations, using this, this naming system that we gave you for RNS. And in theory, we ought to have the same situation with nitrogen. What if we have 4 things on nitrogen that are different? So for example, if I come over here and I look at this molecule down here, this is methamphetamine, Breaking Bad. This carbon atom over here is a stereogenic center. So that carbon atom has, and I'll go ahead and draw, there's an H there, we usually don't draw, but that's a stereocenter. So let me just go ahead and label that. I won't write stereogenic, I'll just write stereocenter here. That carbon atom is a stereogenic center. But this one over here, this nitrogen, that has 4 different groups that occupy space. It's got a lone pair. Let me put the lone pair in one of these orbital-like shapes here. And that is not a stereogenic center. And so how can that be? I mean, those groups, the methyl, this phenylpropyl group, the H, the lone pair, they all occupy different regions of space. We could assign RNS configurations to that, and yet we do not consider that nitrogen a stereogenic center. And let me contrast that. Let's contrast that situation with a quaternary ammonium salt, which we're not going to talk a lot about in this chapter. So it's kind of ironic that I started off with that slide with Jack holding that bottle up. We won't spend a lot of time talking about quaternary ammonium salts, but if you do have 4 different groups on this quaternary ammonium salt, that is a stereogenic center. And we could assign RNS configurations to that nitrogen in exactly the same way that we do with carbon. Okay, so why is it that we don't consider methamphetamine nitrogen a stereogenic center? Or any nitrogen that has a lone pair on it as a stereogenic center, even though it has 4 different groups? Boy, this happened last time. I'm going to have to complain about this. I don't know if this is... try unplugging and plugging here. I apologize, I don't have any control over that. It could be that this cable is worn that's here in the lecture room. Okay, so amines, what's up with that? How can they not be stereogenic centers? They are in fact stereogenic centers, but I'll show you why we don't consider them to be stereogenic centers. I'm going to draw an amine here that has 3 different groups and a lone pair in addition to that. So here's one that has an R group, any R group that's not methyl. So I'll just put CH3 here. So the R could be ethyl, propyl, butyl, isopropyl, T-butyl, hexyl, just anything that's not methyl, so it's different from methyl. And then an H. So that now has 4 different groups. One of those groups is this lone pair. And I can assign Kahn-Ingold Prelog configuration to that. That would have the R configuration. You can go back to your Chem 51A first quarter stuff to remind you of that. That's not one of the things I'm asking you. If you've noticed, I haven't asked you to assign RNS configurations to things in this class. That's not really the most important part of the things that we're doing here. But if you wanted, you could assign an R configuration to that. And the reason why we don't consider this to be a stereogenic center is because very fast, so quickly, these things will isomerize. I'm going to draw the other enantiomer way over here. There's a very rapid isomerization, an inversion of stereochemistry at that nitrogen center. Zillions of times a second, this nitrogen will invert and completely lose any memory of what that stereogenic center was. You can't stop this from happening. I'll go ahead and show the transition state here. It goes through a planar transition state. No carbon atom with 4 bonds can do this. Right? You can't just go through this easily through this type of planar transition state here. I'm trying to draw this planar. And that lone pair is going to exist in a p-type orbital. I'll put 2 lone pairs in that p orbital there like that. So this is the transition state. It goes through a planar nitrogen. And it's reversible, so very readily reversible. And that's fast. You can't stop that inversion of configuration when there's a lone pair on nitrogen. And if there's no lone pair, as in the case of this quaternary ammonium thing, it can't invert like that. It's only when there's a lone pair on there that that inversion is rapid and reversible. We never had to worry about this with oxygen because you can't have 4 different groups on oxygen. You're always going to have 2 lone pairs on oxygen. So this is a new thing. So you'll see nitrogens that look like a stereogenic center, but when I ask you on my exams, clearly indicate stereochemistry and the presence of stereoisomers, you don't have to assign dashes and wedges to amine nitrogens because we don't consider them to be stereogenic centers. And the lingo that we use is we say they are not configurationally stable. So if you have an R configuration, right, you immediately have a mixture of R and S because they zillions of times a second they're inverting back and forth. You know, people ask me, are you going to put spectroscopy on the exam, or are you going to... I'm never going to tell you what I'm going to put on my exam. But if you look at my past exams for the past century, there always seems to be a spectroscopy problem on there. So I think spectroscopy is important. Unfortunately, as I'll show you, there's not a lot you can do with the spectroscopy of amines. And I tend to tell you that, wow, carbon NMR is a lot more useful than IR. But here's one of the winning cases where IR has some information that you can't easily get out of carbon NMR. And that has to do with the number of NH stretches. So I'm showing you down here 3 different amines. They all have the same, basic structure in terms of the connectivity. So here's a molecule that's a tertiary amine. Here's a molecule that's a secondary amine with 2 alkyl groups on the nitrogen. And here's a molecule that's a primary amine that has only 1 alkyl group attached to the nitrogen. So tertiary, secondary, and then primary. But what we're really looking at here, instead of focusing on the alkyl groups attached to the nitrogen, I can distinguish these by looking at the IR spectrum based on how many NH stretches I see. So let's go ahead and take a look at the actual IR spectra of these molecules. And what you'll notice here is even in a molecule that's supposed to have no NHs or OHs, you can still see in this actual spectrum there's this thing here. And that's just contaminating H2O. There shouldn't be that clumpy stuff in there. It's very hard to get rid of all the water molecules when you have a sample. You can have a sample that's 99.9% pure amine, and that 0.1% water has such powerful stretching absorptions that it'll look like there's a lot of it, even though there's a little bit. So there's really no distinctive NH stretches in here beyond that water contaminant. And all of these spectra have a little bit of lumpy waterness in there, that lumpy water OH stretches. The broadness is because of the hydrogen bonding. Okay, but when I look at this NH compound, this secondary amine over here that has this one NH stretch, I can see a peak here sticking above that water lumpy thing that has a single peak. And that's that NH stretch. That's that vibration of the NH as it absorbs IR light and causes that stretching transition. When I look over here at this primary amine that has two NHs, it's primary because there's one alkyl group, but that means there's two NHs on there. Look at how many of these little blip NH peaks I see. 1, 2. See how easy that is? I can just look at the IR spectrum and tell you how many NHs there are on my amine. And that's pretty valuable because you're not going to have any other simple way to get that information. The IR, this is a valuable feature of the IR spectrum. So that's little one blip peak for one NH and 2 blip peaks for the 2 NHs, and then nothing really for there's nothing really for the tertiary amine, whether that's triethylamine or some other tertiary amine. Okay, let's talk about the other types of spectroscopy that we more typically rely on when we try to assign structures. So, I often give you carbon-13 and proton NMR data, and unfortunately, these are not in any way useful for you deducing the structure of an amine. You can't tell something is an amine by looking at the carbon NMR. You can't tell something is an amine by looking at the proton NMR. You just see the same kinds of peaks you would see if there was no nitrogen in there. So if I tell you something has a formula, C5H13N, about the only thing you can tell me is, well, there's 5 different carbon atoms in there that have single bonds, that are singly bonded. That's all you know. You don't know it has a nitrogen. It's only that molecular formula that tells you that. If I look at the proton NMR of some kind of a molecule that has a nitrogen atom in there, there's nothing distinctive about these chemical shifts that allow you to say, oh yeah, I know there's a nitrogen in there. Without that molecular formula, you would have no idea. So really, what is the most valuable piece of spectroscopic information that tells you there's a nitrogen? It's the mass spectrum. And I don't give you the mass spectra in my class because that's where the molecular formula comes from. If you use accurate mass spectrometry, you can get the molecular formula. And I just give you the molecular formula. So that's how you're going to know there's a nitrogen in there, is from the molecular formula is what tells you. And that comes from mass spectrometry. There's a section in our book that's called Interesting Amines, and it really kind of highlights why you ought to be interested in the stuff in this chapter. You know, societally, the most interesting molecules that we talk about tend to be amines, and mostly amines that come from plants, that come from nature. All of these molecules down here, I think with the exception of methamphetamine, these are a class of natural products that you get from plants called alkaloids. So plants are very good at defending themselves by producing things that are toxic to other organisms. So here's a molecule called conaine. I'm not an expert on Greek history or something. I think Socrates was forced to commit suicide or something by drinking hemlock. That's conaine. That's the toxic alkaloid in there that causes people to die. Nicotine you may be familiar with from vaping or smoking cigarettes or cigars or whatever you smoke. That's the stuff that really amps you up, helps you study longer and stay focused, and highly addictive, by the way. And then there's mescaline. So if you've ever gone on a peyote bud trip, maybe last weekend or something, so that's the peyote cacti have this compound mescaline in there, and they're all active on neuronal signaling. Methamphetamine, we'll talk about that a little bit more later in this quarter. That's speed. It goes by just so many different names, meth, speed. Very simple structure, and it is a member of a class of compounds called phenethylamines. They've got a phenyl and an ethyl group attached to nitrogen. This one has an extra methyl group on there. You guys could synthesize this. You know enough reactions now to synthesize this. Go back to your garage, make a ton of it, and make a bunch of money. Caffeine, That doesn't exactly belong in this class because it's not really an amine. It's a nitrogen heterocycle, and you'll recognize that it's closely related to purines like guanine and adenine, the DNA bases. So it's closely related to the base guanine, except guanine has an NH2 group here. But I think the chemical name for this is 1,3,7-trimethylxanthine. But it does have a slightly basic nitrogen, but it's actually an imidazole heterocyclic nitrogen atom. That's the basic lone pair in that molecule. Heroin is a synthetic compound. It's a derivative of the natural product morphine from poppies. Chemists go into the lab and they acetylate those oxygens. We taught you how to do that. I think industrially, if you have a clandestine lab, they use acetic anhydride just because it's cheaper and easier than acetyl chloride and pyridine. But those acetyl groups allow it to just fly across membranes. Man, that makes all the difference why heroin is amazingly potent and morphine is not so much. All right, so these are the common, psychoactive or some common psychoactive compounds. In the laboratory, I've mentioned this over and over, triethylamine is the most common base that we use for organic reactions because it's soluble in organic solvents. Sodium hydroxide, we don't use that. Sodium hydroxide is also a nucleophile. We don't want to mess with nucleophilicity if all we want is a base to pull off protons. So the book just really overuses sodium hydroxide because they think you're comfortable with that, but we don't do a lot of reactions in water when we're trying to do organic synthesis. Okay, and I'm not going to ask you these structures or to memorize these names. That's not really what this class is about. I mostly care that you know chemical principles that you can apply to solve zillions of problems. All right, let's talk about amines as nucleophiles. Boy, the amine lone pairs are way more nucleophilic than oxygen lone pairs. Oxygen, let me redraw those. Those are the worst looking lone pairs I've ever seen. There we go. Okay, nice. Boy, nitrogen is less electronegative than oxygen. Oxygen's electronegative. Oxygen doesn't really want to use its lone pairs to attack things. Oxygen likes having those lone pairs. Nitrogen, not so much. Nitrogen is not as electronegative, and it is happy to take that lone pair and attack things. So you may be itching to use that for an SN2 reaction. So let's go ahead and talk about that. If you take an amine, and you take a nitrogen lone pair on an amine in the presence of some sort of an alkyl iodide, alkyl bromide, alkyl tosylate, you'll get SN2 reactions to occur. And those will be quite facile and quite fast. Now, unfortunately, I'm not going to spend any time talking about that. You're also going to end up with E2 elimination. But let's just set that problem of competing elimination aside. But we'll acknowledge that it's occurring. You'll also be eliminating H and I to give an alkene. But you will get this rapid attack. Now, unfortunately, this is not a useful process. And I'm going to tell you to avoid using SN2 alkylation of amines as a way to make nitrogen-carbon bonds. So I have to explain to you why, even though this is a fast process, it turns out not to be synthetically useful. And this is going to take a little bit of time to explain. So the initial product that you get when you do an SN2 reaction with an amine is you get the ammonium salt. Those two H's are still on there, right? We haven't done any deprotonations yet after we do this displacement of the iodide. So the initial product is this ammonium salt, and that's just going to be floating around there. And it would be great if the reaction stopped right there. But it doesn't stop right there, because the instant that you generate one amine, we still have other amine molecules that haven't yet reacted. So you've got one molecule of your ammonium product here, and you've got 10 to the 23rd molecules of amine waiting to react. And there's going to be a fast acid-base reaction that you can't stop. You can't stop proton transfers. This is always faster than a tachyc carbon. You can't stop proton transfer from your initial product to other molecules of your starting material. And this has devastating consequences for your hopes to get a clean reaction, because you're doing two bad things at the same time. First of all, you're taking your starting material and you're now removing the proton. You're taking away the proton from your starting amine. So this ammonium salt that you just generated is no longer nucleophilic. It's not a nucleophile. It's just stuck there. right? You want your starting material amine with one alkyl group to attack things, but now it can't attack anything. But at the same time you did that, you now just unleashed your product, which has a lone pair on there. Let me just put that lone pair in black. That lone pair on your product is now ready for more nucleophilic reactions. Right? Even if you don't want to put a second ethyl group on that nitrogen, it's going to make a second ethyl group, bond to an ethyl group. So this is the problem. Let's go ahead and watch that. If that ethyl group, the second you release this ethyl group, now you've got two different amines floating around that can attack the ethyl iodide. I'll go and draw a note. Like if there's an ethyl iodide molecule on there, yeah, you want this lone pair to attack that ethyl iodide. Problem is, now you've got another amine reacting, and it's going to attack it even faster. Let me change this to my red pen here. Just a little bit faster, close to the same rates. You don't want this to happen, but you can't stop it from happening. So now instead of just getting one bond to an ethyl group, now we've got products in there that have two ethyl groups on there. And we didn't want that second ethyl group, but you're stuck with it. And that's still floating around with more molecules of your starting amine, unfortunately. And so we're going to end up with more proton transfers that you can't stop. Fast proton transfers. Proton transfers are fast. Attack at carbon is slow. You can't stop this acid-base equilibration that's occurring. So up on top here, you can't stop this acid-base equilibration. You can't stop it once we put two ethyl groups on there. And so now we have three different things floating around in our reaction mixture. Now, every ethyl iodide molecule is going to run into regular amines, amines that have one ethyl group, and amines that have two ethyl groups. And this amine that has two ethyl groups can react further. You can't stop this from happening. It's like every ethyl iodide is now going to see this tertiary amine and think, oh, maybe I'll react with that. And so here's yet another product that you don't want, but you're going to get it in your reaction mixture. Now, thank goodness, this is where it stops. You can't really go any further. There's no acid-base reaction you can do. If I were to draw out the actual product, there would always be an iodide counterion associated with that. So now, the product that you would get out of this reaction would be a mixture of all these things. It would be a mixture of these things, all in here, floating around. And this is why I tell you don't use alkylation of amines as a way to make carbon-nitrogen bonds, because of this problem. I'll show you one potential trick, but it is not a trick that is efficient. It's a trick that is intrinsically inefficient. And so let's go ahead and see one way to get anything useful out of this type of chemistry. But it's a pretty obscure situation. It's not a general solution to efficient organic synthesis. So here's one proposed solution to this problem that the book shows you. And they work this left and right, trying to make you think that it's general, and it's not particularly general. So here's one thing that you can do. One thing that you can do is you simply use a vast, vast excess of your amine. That way, as soon as you generate your amine, the chances are far more likely that your next alkyl bromide is going to come in contact with this because it's present in vast excess. If you have 1,000 equivalents of the amine, or 10,000 equivalents of the amine, if you generate one molecule of this, your alkyl bromide is more likely to be attacked by the abundant amine. You just use a vast excess of the amine. And then when you're done, you throw away the leftover amine. Right? You just use an excess. Now the problem is this is only useful when your amine is dirt cheap, and that's pretty much only ammonia. So this really only works with ammonia. You can't take complex organic molecules that cost you money, that cost you any significant amount of money, and use them in excess like this. So basically, this is not very useful for anything other than ammonia as a general solution to how to make efficient bonds using SN2 reactions. And what I'll hope to convince you when we come back on Monday is that there are much better processes that are not SN2 for making carbon-nitrogen bonds. But if you have to use SN2, this is a trick that's possible. Let me show you one other way to use SN2 reactions to get an efficient yield of the product, to efficiently convert starting material to product. And this one is not very general either. And the idea is you take, okay, if you want to make bonds to this, and you don't care what kind of bonds, if you use an excess of the alkyl bromide, it will keep putting methyl groups on that nitrogen until there's no more lone pairs left over. So just by using an excess of the methyl bromide or the alkyl iodide or the tosylate, you can convert that to a quaternary ammonium salt because there simply won't be any more lone pairs left over. But it's not that often that you're synthesizing quaternary ammonium salts. I showed you those examples of benzalkonium chloride and those fungicidal, antiseptic sprays, but it's not that common on pharmaceuticals or on biological drugs to have quaternary ammonium salts. Okay, so those were two examples of how to use SN2 alkylation of an amine. They're not particularly general. And I'm going to show you one last trick if you just have to use SN2 reactions for how to do it efficiently. And it's not that common of a trick anymore, but this used to be a common way. And I'm not even sure, I don't even want to take the time to explain to you what this has been replaced with over the past 40 years ago. Okay, suppose you wanted to do an SN2 reaction, or you wanted to do some sort of a transformation, and the only reagent available to you is this alkyl bromide, and you wanted to put an amino group where that bromide is. I'll show you a trick for how to do that. So one trick we showed you was use a big excess of ammonia. Okay, that would work. But here's another trick that people use. And there will be cases that I'm not going to go into where you just can't use a big excess of ammonia. We need another nucleophile that can alkylate once and only once. And I'm going to show you a nitrogen nucleophile, a special nitrogen nucleophile that can alkylate once and only once on the nitrogen atom. And it is a species called an imide that has been deprotonated. And specifically, it's an imide anion. This functional group with two acyl groups on the nitrogen, that's called an imide. And so this is an imide anion. Leave some room. I'm going to give you the prefix for this in a minute. So this would be referred to as an imide anion. And because there's a benzene ring on there, that makes this a very specific one. This is a phthalimide anion. We don't pronounce the pH part. You just pronounce it like it's phthalimide, TH. You only pronounce the TH part, or otherwise your tongue would get twisted up. So we use a phthalimide anion. It doesn't matter whether you use the sodium salt or the potassium salt. And this is very easy to make. And because of those carbonyl groups on there, you can only alkylate this one time, right? This negative charge on here, it's not like a regular amide. It's not an amide, it's an imide. You've heard of an imide before, N-bromosuccinimide. Has nothing to do with this. So, but if the word imide sounds familiar, that's because we've talked about N-bromosuccinimide for free radical brominations before. But that has nothing to do with this. Okay, so this is the phthalimide anion, and if we put this in with some sort of an alkylating agent, an alkyl bromide, an alkyl tosylate, an alkyl iodide, we can do SN2 reactions with these phthalimides. And it adds once, and it adds only once, and it stops. And you can't do that with a regular amine. So now we've efficiently made this carbon-nitrogen bond where we've added one and only one carbon-nitrogen bond. You get this, the Br minus doesn't matter. Okay, so we've made our carbon-nitrogen bond. But unfortunately, you don't really want all that phthalimide, phthalic acid thing on there. We wanted an NH2 group, so we've got to get rid of these amide bonds here. So this is now just a regular, it's an N-alkyl phthalimide would be the description. We're going to use the same hydrolysis conditions for this that we used for hydrolyzing amides. And the most common ones are the basic hydrolysis conditions. Sodium hydroxide, it is hard to hydrolyze amides. Water and heat. Boiling it. And not just 1 molar sodium hydroxide, 4 molar sodium hydroxide. It'll etch your glass bottle if you leave solutions this concentrated sitting in glass for a year. So that kind of sodium hydroxide is really concentrated. And that's what cleaves these two amide bonds. They're imide. It's an imide. But the two bonds are kind of like amides. So the book often will try to just write hydroxide and water, but I've already told you I very specifically want you to talk about the conditions for amide hydrolysis, showing actual species like sodium hydroxide and clearly indicate that there's heat in there. And this is why this is not used that often anymore. The conditions are brutal. We have better ways to make carbon-nitrogen bonds nowadays. Okay, this is called, this two-step process of using a phthalimide anion and then hydrolyzing the phthalimide group off. Let me show the other byproduct of this process in case you're wondering what happened to that benzene ring piece. That ended up generating the anion of phthalic acid. So this other piece you just throw away. And if it was done in sodium hydroxide, you'd have sodium counterions associated with that Na+ over there. So that you throw away. This is called the Gabriel synthesis, and it's a bit archaic now. We have other ways to do this, but this is exactly the kind of question they would ask you in the MCAT or the DAT. They haven't seemed to move into the current millennium here. All right, when we come back, I'm going to show you some more useful transformations of amines when we come back on Monday. The ones that I just showed you today are not really the typical transformations that you use to make carbon-nitrogen bonds. SN2 reactions are not the best way because you always have to worry about elimination, E2 elimination, competing with SN2. So when we come back, I'll remind you of some reactions to make amino groups, hydrogenation of nitro groups, which you've seen, lithium aluminum hydride reductions of amides, which you've seen. A lot of it is just review, and I'll show you a couple of new tricks for making carbon-nitrogen bonds. All right, you guys have a great weekend, and I will see you on Monday.